And we are live.
Great. Okay, so folks are going to start coming in to the Zoom. Folks coming in, joining us live on YouTube as well. Welcome, everyone. We've got another exciting Weights and Biases Deep Learning Salon for everyone. I'll be speaking in the second half of the salon, so that's exciting. I talked last about a month ago, and it just was so much fun that I decided I'd do it again. Before we dive into that, and before I introduce our speaker for this week, I wanted to talk about the upcoming salon. So November 24th, Thanksgiving week in the United States, we're going to have two folks on to talk about benchmarks, to talk about two tasks that they want community input on, sort of an opportunity on a shared leaderboard to contribute to two different projects. And I'm actually really excited about these two benchmarks in particular, because they're both sort of oriented towards a more thoughtful, maybe more ethical AI. First, the Safe Life benchmark by the Partnership on AI, which is explicitly about safety and limited side effects in deep reinforcement learning. And then the Deep Form benchmark. So this is from a group that's trying to get a better handle on who's spending money on political TV advertisements from this sort of vaguely structured form data. So extracting information from forms is really, really hard, and they built this benchmark to try and learn a little bit more about it. So that will be 2 weeks from right now, November 24th at 5 o'clock Pacific time. And the RSVP link for that will be tiny.cc/WB-salon. You can RSVP for that starting about 10 minutes from now. And we do the salon every 2 weeks. You can catch the salons you've missed on our YouTube channel. We've also got some app tutorials and introductory and advanced lectures in machine learning if you want to check those out. We've also got a Slack forum you can hop into at bit.ly/Slack-forum. Those links will pop up in the YouTube chat and in the Slack chat in just a minute. So that's the future of the WNB Salon, but let's talk about the present. Presently here, we have Chirag Agarwal, who is joining us from Harvard, where he is a postdoctoral scholar and did some really exciting and interesting work on using the variance of the gradient, something people don't normally track, don't normally think about, to track something that people do think quite a bit about. Where are the outliers in my data set? Where are the examples my network's not learning, about? Which ones are they? So I'm really excited to have Chirag on to talk about that work.
Awesome. Thanks for the introduction, Charles. I think that was a better introduction to the work that I could have come up with. So I'm going to steal that from you now. So, okay, can I share my screen now?
Yeah, go ahead.
Awesome. So it looks good. Awesome. So yeah, hello to everyone who are attending today's Weight and Biases Salon. I would start by thanking Charles for inviting me to the salon today. In today's talk, I'll be basically discussing about the work with my fantastic collaborator, Sarah Hooker from Google, about estimating example difficulties using variance of gradients. So I guess before going to the depth of the work, I would like to just provide some basic motivations for studying the relative importance between different samples during the training process. So understanding individual samples' importance is very important, given that modern data sets are large, with sometimes data sets like ImageNet, they comprise of more than 1 million of images. So this is not feasible for an individual to look at individual explanations of each data point in these huge data sets. Moreover, it is also critical to understand the relative importance of individual classes and inspect images that the model finds easier or more challenging. Last but not the least, most of the current works in explainable artificial intelligence, XAI, are focused on explaining model behavior on single or a group of explanations. However, these don't actually highlight the inherent bias of the model towards features like, say, colors or textures in an image classifier model. So these were like the motivations that prompted us to move into this direction and explore the variance of gradients. So with respect to explanations, most of the earliest work in XAI was based on model gradients. Now, using vanilla gradients is intuitive as they have a very clear connection to the neural network function. Basically, we have an image, let's say. We can easily calculate its vanilla gradient by backpropagating the loss with respect to the input image and get these gradient representations of the model. However, following works showed that gradients are very noisy and hence uninterpretable. This led to several works which tried to improve the gradient maps by either smoothing them or using methods like guided backpropagation or trying to integrate the gradients between a baseline image, let's say a gray image, and the input image, here the image of the dog. As one would observe in all these different gradient maps, what most researchers were trying to do was to tune these gradients so to give them some interpretability with context to the raw vanilla gradients so that these maps can be understandable to end users like us, humans. However, one may also question that the gradients can be the best explanation of a model because that is what the model uses to learn the given objective function, right? So this actually brings us to why variance of gradients. And as I said before, the raw input vanilla gradients can be the best explanations of a model in some context. So we hypothesize that gradients of examples that can be easily learned by the model will converge quickly during the early training of the whole model, as compared to the challenging examples where the gradients could not converge quickly. So following this hypothesis, what we basically do is we calculate a proxy metric that's like the variance of gradients for quantifying the relative importance between individual samples of the training and the testing data sets. In this figure, we basically show an input image that's the image of the bird, and we show its gradients as it is evolving during different checkpoints to the whole training process. This image was taken from the image dataset, and hence it was trained using a ResNet 50 architecture for 90 epochs. So we can easily calculate the gradients with respect to any particular checkpoint throughout the training process. And that's like one of the best USP of using VOG score. So using these gradients, we come up with this VOG scalar score. In the given equation, the STI basically represents the gradients of the particular image at the given checkpoint T. Mu I is basically the mean gradients of a given number of checkpoints. Here, since K determines the number of checkpoints across which we are trying to calculate the gradients, and N determines the number of number of pixels in the whole images. So in a way, we can actually interpret the VOG score as a scalar score, which represents the VOG across each pixel of the image. And then we basically take the mean across the whole VOG across all pixels to get just one scalar score for a given input image. So what we do then is calculate these VOG scores for all the training and the testing images in the dataset by using the different checkpoints of the model. So many existing works have shown that there exists different stages of training during a deep neural network. So what we show here is on analyzing the images using the VOG score, we see that images having low VOG scores are very different than the images which are having high VOG scores. In this particular figure, we trained the ResNet 18 model on C400 dataset, and we tried to visualize the relative importance between the apple class images. Clearly, we see that there's a big cluster of red apples which have a low VOG score as compared to the high VOG score apple images, which are more cluttered. And in some of the images, there are like multiple apples. On comparing this to the late stage training, we see similar patterns where the low VOG score images are more object centric and have clear view of the object in interest, that is apples, whereas the high VOG samples are more cluttered and they are taken from different vantage points. So one quick question that would come to any model developer or end user is, can we use VOGs to have a relative ranking across each classes? So in this particular experiment, we divided the training process into two stages, which is the early stage and the late stage, comprising of three checkpoints. The proposed VOG score then actually discriminates images with clean and cluttered backgrounds, and higher VOG scores images are usually images with zoomed in view, or they are more atypical as compared to low VOG scores. In this particular image, we trained a ResNet 50 architecture on ImageNet dataset, and we basically visualized the cluster of images belonging to the MagPie class. Very surprisingly, we see the same pattern as in the CFAR datasets, where we see the low VOG samples are much more cleaner and have the birds centered to the images as compared to the high VOG scores, where you'll see zoomed in views of the bird or cropped images, which are basically the data augmented portions of the datasets. We saw the same pattern for a different class, which is the pop bottle in this case, where the low VOG scores had images comprising of multiple bottles in the same image, whereas the high VOG score had pop bottle images where, let's say, a human was involved, or they were taken from the top view, and all the different styles of pop bottle images. So these qualitative insights gave us good motivation that VOG can be actually used to understand the different clusters of images during different training process, different training stages, and for different classes too. So moving on to some quantitative results, here we show that VOG can discriminate easy and challenging examples easily. We trained CFAR10 models, and it achieved a testing accuracy of 89.55%. It is to be noted that all the models that I'll be showing now were trained with 100% accuracy. That is, there is some sense of overfitting across all these networks. So we clearly see that the misclassification rate is the highest for the VOG scores, which for the samples which have the high VOG scores. Interestingly, we found the similar patterns across two more data sets of CFAR 100 and ImageNet. Here, if we see carefully, then the testing accuracies of the CFAR 100 and ImageNet datasets were much lower. Hence, that means they were more overfitted. And as compared to CFAR 10, that is why we see a much more linear pattern between the VOG scores and the misclassification error rate, where we see a consistent trend that as the VOG scores increases, the misclassification error increases. So these are all good because we can easily use VOGs to understand the testing data sets. But now moving back to the training data sets, then we ask the question that, can actually VOG give us more insights about the behavior of the model during different stages? So we took the ImageNet trained ResNet 50 model, and we saw that the behavior completely flips in the early and the late stage. Now, the correlation pattern with accuracy reverses as we see from the early to late stage training, which gives us an interesting viewpoint into the training dynamics of the model. That is basically that early on, the gradient updates have high variance for the easy examples, but once they are being trained, their VOG scores decreases, and later on during the late stage process, the gradient variance is high for only those samples that the model finds challenging. So these were more like looking into a trained model, be it the training data sets or the testing data set. But an interesting application that we thought VOG can be used to is that it can act like an unsupervised auditing tool. Now, it is to be noted that all the results that we have seen until now, the gradients were actually taken using the ground truth class of the particular image. But in real world setting, we often do not know the ground truth class. So the question comes that, can VOG serve as a good auditing tool if we don't know the predicted class, or if we don't know the ground truth class of the respective inputs? So what we did here was we took the backpropagated gradient with the top one predicted class of any image, and then we tried to visualize the low VOG and the high VOG samples. To our surprise, we actually see the similar patterns as we saw for the ground truth VOG scores, where we see that images that were correctly predicted by the model were more object-centric as compared to the high VOG samples, where we see blurred out images or images where the object was too much zoomed in. And, and hence, I mean, that gave us a good indicator that VOG can actually serve as an unsupervised tool, since we do not use any ground truth information of the respective images. Now, all these results are fine, but uh, to build trust with any end user, or even if you're giving a model developer this VOG proxy metric to analyze the model, a key desirable property for any tool would be the consistency. That is basically that we would expect a consistent method to produce a ranking with a very closely bounded distribution of scores across independent runs. To measure the VOG stability, we train five ResNet 18 models on CIFAR 10, and then we try to visualize the VOG scores across each of these five different trained models. Uh, all the five models were randomly initialized, so we can expect some variance. But when we visualize the VOG scores with respect to the error performance of these five models, we saw more or less like all the VOG scores had the same patterns across the five models, which talks about like the stability of the VOG metric. So these were like basically all the results that I could have summed up today for this talk. So the final takeaways for this VOG paper was that it can serve as an interpretability tool for ranking both training and the testing samples. An interesting advantage of VOG is that it does not need any modification of the architecture, since we always train models and we always capture snapshots during the training process. So it doesn't come with any external additional costs. We can easily just take snapshots of a trained model and then calculate the VOGs of the input images in this case. And the third takeaway would be that the VOG scores can actually aid us in clustering images with respect to each class across the training data sets and the testing data sets, so that we can actually understand the behavior of the model and also know about the dataset bias, whether for say it consists of images of just one unique nature, or it can have a good diversity across in each image class. So I think those are like the final takeaways of our work. And yep, you can find our paper on arXiv, and yep, I'm open to questions now.
Great. Thanks, Chirag, for that nice overview of your work. So I have a lot of questions. I encourage folks on Zoom and on YouTube to also chime in if they've got questions of their own. So either in the Q&A on Zoom or in the live chat on YouTube. So I guess just to start us off here,
Right.
so how many samples from a class do you need in order to do this variance of gradient operation?
So that's an interesting question, Charles. So thing is, we actually experimented with different checkpoints, but we actually found out that as low as just 3 checkpoints from a model can actually can lead to a good VOG approximation of the whole data set. And in all these results that I presented today, we just took 3 snapshots of the model. Like by that, I mean that during the early stage, we just took 3 snapshots when the model reached decent accuracy for the testing model, for the training data set. And then we, let's say, took the last 3 checkpoints during the end cycle of the training process. So yeah, we just used 3.
I see. And can you clarify? So if I have a single example, I'm going to have, I'm going to have a variety of like gradient values if I backpropagate all the way to the pixel level input.
Right.
But that variance isn't what you need. What you need is variance of the gradient over time through training.
Exactly. So what you just described would give us like the gradient for each snapshot. So that would be like basically the gradient heat map of that image at that particular snapshot. But what we are trying to do here is we're trying to calculate the variance of those heat maps gradient heat maps in this case across all the different checkpoints, and then calculate the variance.
I see. And one set of questions I really wanted to kind of dive in a little bit is what you can do with this variance of gradient just on the basis of like without doing any training, actually. So like at the very beginning, I haven't done anything with my data set. I have a random network.
Right.
Like, would you be able to look at the variance of the gradient like across random initializations to get a sense for something like this metric? Or is it really important that it's the same network, the same architecture over time?
Right. So if I understand the question correctly, are you asking whether VOG can serve as a prior information before the actual training starts?
Yeah, that's the general direction I'm pushing. And the first idea I had in that direction was just like, let's try 5 different random initializations and do
Right.
VOG across that.
That's a good question. So we did try this thing up, but actually you actually presented a good point here. So what you're basically saying is in the stability experiment, we trained 5 different models. What you're basically suggesting is we don't train them, we just initialize them and calculate the VOG for the uninitialized model. But then my question would be, if you're not training, then how would you calculate the variance? What you will be basically getting is the gradients for each of those random initializations. Then we can always do the variance across all the 5 different initializations. That is something we can do. But then again, if we do that, then that would not be pertaining to one particular model. That would be like the variance across 5 different runs. Right? So
Yeah, I guess the intuition that I kind of have here is, I guess, yeah, the idea is that the example sort of maybe jumping across a decision boundary or something like that, right? And I
So,
suppose, yeah, for different random initializations, maybe you would expect there to be a lot of jumping across decision boundaries, which you wouldn't expect for the same network over time.
that's true. And moreover, for a randomly initialized models, it would be very interesting to see the gradients for each of the inputs, whether all of them will be random or there will be some. It's like many works have also showed that even randomly initialized models can serve as good features for the like there was a paper on deep image prior, so they also show that randomly initialized networks also have some certain characteristic. So in that essence, I guess it's interesting to do this experiment, right?
Relatedly, I think people have found that random networks, if you look at the gradient maps for random networks, those like the things that you presented at the beginning, either the raw gradient maps or something like smooth grad or integrated gradients, you do see a lot of structure even with a randomly initialized network when you do that.
We do some, but the images that I showed earlier were for trained models.
Yeah. This is something so I worked on interpretability for a little bit. And one of the things that was important in our application was we wanted to demonstrate that like it was different from a random network. And I found at least some people reporting that there was much higher overlap than you would expect by chance. It's not the case that the gradient map looks random. It sort of concentrates on things like the center of the image and the highest contrast regions of the image and things like that.
Right. Yeah, that's a good point. And I think, yeah, that would be interesting to see whether those things actually carry forward to all the images in the particular class. That would be interesting.
What possibilities are there for applying this in, just to start off, like a regression problem based off of computer vision, like a bounding box thing? Like obviously you no longer have the class to like organize things by, but would you be able to detect maybe more difficult examples or something like that?
That's a good question, actually. So we haven't looked into it right now, but I clearly see that we can easily use the same formulation here. But in that case, basically we backpropagate the gradients, not with respect to the ground truth class, but here, as you're saying, we have like, let's say the bounding box coordinates. So we can easily backpropagate the loss using the difference in the coordinates or using the ground truth bounding box or the predicted bounding box. So I think in that sense, it can be used for object detection or image segmentation, those all kind of those different tasks.
Gotcha. And what about in application to different domains where there is also a class, like say like audio classification or sentiment analysis and NLP, something like that?
Yep, I think that's I think I don't want to sound very philosophical, but I think that's the beauty of VOG in this case, that it does not take anything from the model or the architecture. It just uses the gradients. So in any application or domain, as you're mentioning, if we can by any chance calculate the backpropagated gradients, which is the main point in all deep networks, that we use the backpropagated gradients. So any application doing that can be easily use VOG as a proxy metric.
Mhm. So I guess the question I have is, do you have any indications that it'll work just as well in one of these other domains? Because, it's not guaranteed that necessarily something, maybe it's very important that there, say, these max pooling operations that you find in convolutional networks to make this work really nicely or something
Right.
like that.
So I myself haven't tried this other applications, but we have received some emails regarding interested researchers applying it to sequencing data or segmentation models. So yeah, people are using it as for different applications.
That's exciting. I think, yeah, the emphasis, I think, was in your talk was on a lot of the the data set cleaning kind of side of things, or the outlier
Yeah.
detection kind of side of things. Can you talk a little bit more about how you think
Mhm.
variance and gradient could be used for the like explainable AI side of things?
So that's a good point. So in this case, you're right. Most of our results were actually focused on detecting out of distribution data or atypical examples during the training process. With respect to explainability, so the gradient maps are itself, as I said, like in 2013 when the work started, people actually felt that gradients can be the best explanation to a model, which some people still believe that, because that is it has a clear connection to the model, right? So in that case, we're actually using some notions of explainability in this case. Now, the other point that you brought up is, can we use, rather than using just raw gradient maps, can we actually use these different variants of gradients, like the smooth grad or integrated gradients, and then calculate the VOGs on those XAI based heat maps algorithms? So that would be something interesting to try.
I see. Yeah. So the idea is it's like a variance of the map over time, and that doesn't have to be the gradient. It could be any other map that you
Exactly.
apply.
So exactly, that's the point. So right now we are just taking the vanilla gradients, but yep, we can always try to extrapolate other gradient based methods on this.
That's yeah, interesting. So I guess in the last couple minutes of your time, could you talk a little bit about
Mhm,
sort of the future directions you see you taking this work,
mhm.
and maybe your career in ML?
And so I'll try to make it brief. So with respect to VOG, I think there are a few interesting directions. Some of them, as we discussed, that can be actually use VOGs, the results that we have for our image classifier, and then use it for different applications and other domains also, not respect to just images, but let's say language models and graph networks. And that's like one very promising direction. And other one is also to use the VOG scores and understand the training on the fly, and basically leverage the VOG scores to improve the training performance of a model. So that would be interesting direction.
Hmm. Yeah, that does seem. Yeah, there's a lot of room still, I think, to improve what people do during training. For things, out of distribution data is a hard. It's not something you're just going to resolve with normal gradient descent. So
Exactly.
that sounds like
Yeah.
a great direction to
Right,
take things.
right, right. Exactly.
All right. Well, thanks for coming on, Chirag, and thanks for presenting thanks for doing some really great and interesting research and being willing to present it to us.
Thank you, Charles, for inviting me today. It was a pleasure talking to you.
Mm-hmm. All right. Take care, Chirag.
Bye.
All right. Peace. I am actually normally this is where I would introduce the next person, and but the next person is me. So I guess I'll hop right into my presentation
Sure.
and take over the screen share. Great. All right. So what I wanted to talk about today is one of my sort of favorite test problems, one of my favorite sort of basic, simple examples that I have in my head when I'm thinking about neural network optimization and neural networks in general. So the motivating idea here is that neural network optimization is really complicated. It's got a lot of pieces to it. And even though it might feel easy now, it's not actually that easy of a thing to do. So, nowadays we've got so many good architectural ideas. We've got so many good just sort of, built-ins in the neural network libraries that we use, like PyTorch and TensorFlow, that it doesn't strike us as that difficult to spin up a neural network and train it on something like image classification. And this is something that the optimization for deep learning review paper by Ro-Yu Sun at U of I handles really or mentions, and I think makes a good point about that. If it was 1980 and you sat down to try and solve an image classification problem with neural networks, you probably would fail because you don't have all these nice things in your toolkit that we have. And so because of that, I think it's easy for us to forget that there's a lot of complexity underneath something like dot fit. And so when it comes to trying to understand something difficult in mathematics, which is in the end, I think, one of the best ways to understand what's going on in deep learning in this numerical computing kind of field, I think the most important thing that is underappreciated by people who come from a software background is the importance of simple test problems. And so I think there's a really great explanation of this that I got from a friend who finished their PhD in math at Berkeley around the same time I was doing mine. And what they said was, everyone I know who does math does basically the exact same thing to make their lives easier. Whenever they hear a conjecture, somebody's thought about how something might work in some branch of math, they compare it to two examples specific to that branch. One that's well-behaved and simple, and another that's pathological and counterintuitive. And if the conjecture is true on both, then it's probably true. And if it's not, then you've got yourself a nice counterexample. So when it comes to trying to understand and think about machine learning, like what's going to work well, what's going to not work well, why to use a particular piece or why not to use a particular piece, or if somebody makes a claim about the nature of deep neural network training, I use the same tactic. And so my two examples, one of them is memorization tasks. That's one of my pathological test examples, that if somebody makes a claim about how neural networks work and how they generalize, I think, okay, does this explain memorization in neural networks well? So specifically, a memorization task is one where you destroy all structure relating the inputs to the labels. So if you were to take, say, the MNIST data set, and then instead of having the actual targets, you just shuffle them. So this little bit of Python code here takes the MNIST targets and replaces them with a shuffled version of them. Turns out neural networks can still minimize the training loss in this example, even though there is no, there's no information there anymore. It's just the labels are effectively random. So this is something that people have demonstrated, and it shows that neural networks are capable of memorizing their data sets, even if they don't necessarily do that in real life. So the two sides of this coin are, you have one example that's sort of the canonical gnarly bad example, and then you have one example that's the well-behaved and simple example. And for me, I use one that is effectively just multiplying by one with a deep neural network. So let's go through this. It's got a mathematical inspiration, and so I took a mathematical approach here. So a fully connected network, let's define that. It's a function of its parameters and its inputs that alternates between matrix multiplication and function application. So it's got all these nonlinearities, sigma 1, 2, up to k, and then it's also got these parameter matrices, theta up to k. And we alternate between applying the matrix to the input and then applying a function to it, a possibly nonlinear function to it. An autoencoder network is a specific type of network, one that compares its outputs directly to its inputs as opposed to comparing them to something else. So D is some function that takes two inputs. If they're the same, it returns 0. Otherwise, it returns something else. And what D is doing here is it's comparing the input X to the output of the network F applied to its parameters and its input X. And that function there that I'm defining here through this is the loss function. It says, okay, the loss function compares the inputs to the outputs. And the loss is what we make small. And an autoencoder, therefore, returns something that's close to its inputs. So the case of autoencoders includes just multiplying numbers by 1 as an important special case. So if we just take all of those functions to be the identity, right? Just take all the nonlinearities out of our neural network, we'll end up with something called a linear network. And linear networks, I'm not the only one who likes to use these as a test case for doing theory on neural networks or for thinking about neural networks. So there's a nice paper by Sachs, McClelland, and Ganguly that's basically what can we do to understand not only how neural networks learn, but actually a little bit of the psychology of how animals and humans learn just by studying what happens in linear networks. It's also the case that networks with rectifying linear units are actually piecewise linear on their inputs. So this gives you a sense of like, okay, if I only change the input a little bit, a rectified linear network will behave very close to a linear network. So it's another reason why this case is useful for helping you build your intuition about what's going on. The difference being that because it's simple, and because it's dropped that nonlinear piece, it's a lot easier to understand. So if we also take another step and make this even simpler and choose the dimension of everything to be 1. So every hidden layer has dimension 1, the input has dimension 1, and so the output has dimension 1. We replace all that matrix multiplication with just a series of things multiplying together. And we get a function looks a little bit like this. I was using this case actually to help me understand JAX better. So that's kind of where this talk came from. And so in JAX style NumPy, that looks like, okay, f of theta and x takes the product of all the thetas and multiplies them by x. It's the same thing as what's written above. And it's got this nice little bit of extra JAX stuff here to make it so that I can now apply this function on a single input or multiple inputs, so batch or non-batch, and I can apply it to one parameter set or many parameter sets all at once. So I can effectively apply 10 networks to 10 data points and get 100 outputs with just the same function that I can use for normal forward prop. So JAX is pretty great, is one thing I learned in the process of building this example. So the reason why I wanted to do this simple setting, and one of the things that makes this a really powerful example, is because it's so simple that we can actually see everything that we normally can't see when we're doing deep learning, for real, when we're doing it on images with thousands of pixels in them and trying to predict one of thousands of classes at the end. The dimension of everything is so big. The dimension of that input X, the dimension of the hidden of the parameters theta, these things are in the thousands, in the millions, in the billions nowadays. And so you're hosed for trying to think about that spatially and for trying to visualize it. But if we, in this case, choose the number of hidden layers to be 1, so there's one hidden layer and then one output layer, and so 2 layers total, then we've reduced this down so much that now there's only essentially 2 dimensions, 2 parameter dimensions to think about. And so anything that has to do with the parameters, we can visualize. We can visualize because we have 2 dimensions for the parameters and then 1 dimension for whatever it is we're trying to measure. So for example, we can look at the network's output as a function of the parameters here. So this is a surface here. So the values there, it gets red as the value gets higher and it gets blue as the value goes lower. And then in between it is gray. And that z-axis, which is also the color axis, is the output of the network on the number 1. So if I put in the number 1 to this network, what do the outputs look like? And it looks like the outputs get big as the parameters have the same sign. So as we go to 2, 2 in the upper right quadrant, and it gets, and similarly, the output gets big if both inputs if both parameters are negative and large. That's the bottom left corner, which is also red. So in order to finally get a loss function and get ourselves to the point where we're looking at a neural network optimization problem, we just need to choose that difference there, that D function that compares the inputs to the outputs. And so if we choose the squared error, then the loss function is just the squared difference between the inputs and the outputs averaged over a batch. That's easy to code up. We just apply the mean of the squared error function like that. And that loss is actually simple enough that it's something we can write out explicitly. So if we just say, all right, let's say that our only input is the number 1, there's only one data point, then if we look at that as a function of theta, let's see what the loss looks like. So first, theta 1 times theta 0 times 1 is what f of theta colon 1 is up there, theta semicolon 1 up there is. That's the definition of what our network does to its inputs. So that simplifies things. And then we can take that and write it out, sort of expand it out if we'd like. It makes it a little bit easier to do other manipulations. And it's very clear now that this is just a polynomial, right? And that's helpful, especially if you have a bit more of a math background, to recognize something that you may have seen in other places in mathematics, in other problems that you've run into. You've probably run into polynomials before, whereas neural networks are maybe a new and curious thing. On the other hand, maybe if you know a little bit less about math and are a little bit less comfortable with polynomials, it's interesting to see that the simplest version of a network, of a neural network, ends up being a polynomial in terms of its loss function. So not only can we write it out explicitly, we can also sort of look at it. We can directly look at it. We can visualize this loss function. So this is the thing that we are moving on when we do gradient descent. This is the thing that we are, because it's in 2D with this one extra dimension, it's sort of a lot more physical, right? It looks a little bit, if you look at it, like a mountain range, right? There's two of those two big red mountains coming up off the side, a nice big valley in the middle. It's a little bit more physical, and we can think about it in these sort of more physical terms. And this, in a way that we couldn't if we were looking at a neural network problem where this is tens of thousands of dimensions. And even more so, we can also combine that with by hand mathematical calculations to get the values of the gradient. So if you crank through that polynomial that we had previously, you can calculate the gradient by hand. Uses only the rules of the gradient calculus for polynomials, which are on the easier side of calculus when it comes to doing calculus. And you can actually get an explicit expression for the gradient. Of course, in Python, we rely on automatic differentiation, but it's helpful, especially in cases where we use automation to take some of the difficulty out of the actual problems we want to work on, to be able to go back to a simple problem like this one and actually crank it out, work on it step by step, and see what exactly is being automated away. And the utility here is that we can actually then look at not just the loss, but also the gradient as an overall vector field. We can look at what the gradient is at every single point and get a better sense maybe for how gradient descent is going to behave. So you can see, if you take a look at this gradient field a little bit more closely, the highest values are very far away from the center, and then the values drop precipitously. So these little tiny arrows represent the gradient at each point. They point in the direction gradient descent would go. So it's the negative gradient. And these, you can see that they're much, much tinier as we get down to the bottom here. So the gradient, the scale of the gradient, it gets really, really big when you're far away from a solution. And then once you get even a little bit close to it, it shrinks back down. So this is something that's going to generally be the case with neural networks. And this is one of the reasons why your loss goes down really, really quickly when you first start, because you tend to start in some area where you're not doing so well. And there's obvious, big gradients that help you improve really, really quickly. So gradient descent is the method that gets used to optimize neural networks, right? We take that gradient and we apply it, we calculate it, take it, scale it, flip it around, and add it to the value of the parameters. So we follow those arrows there that I was showing on that on the surface. And so that looks like, in Python code, it's theta minus eta times the gradient. And it took JAX here, and I actually vectorized that function, which gives you the ability to run gradient descent on multiple networks across batches at the same time, all with the same function that you would use to train one. Again, JAX has some pretty cool stuff in it. Though I feel obligated to point out that some things are a little bit harder in JAX, namely that if you want to try and update the values of the matrix, say pre-allocate memory and then touch it later, JAX makes that a little bit harder. So, I felt like I couldn't be completely positive without pointing out the one place I ran into some trouble. But, that tiny bit of trouble aside, that little detail avoided, it was, straightforward to set up this nice batched gradient descent. So to run gradient descent for a couple of hundred steps from a couple of hundred different positions was pretty fast. And that gave me this visualization here on this one. And you can see a large number of the trajectories are getting sucked towards the center there. So they're getting sucked towards the value 0, 0 right in the middle at the origin. So multiplying the inputs by 0, and that's not what we wanted to do, right? We wanted to get a solution where we multiplied the inputs by 1. We want the inputs and the outputs to match one another. And so just looking at this one, it would look like, okay, well, there's, sometimes when I do gradient descent, it's going to fail on this problem, and sometimes it's going to succeed. And so we can see that if we take a look at the losses over time. So this is the kind of plot that you're maybe actually able to do when you're doing, machine learning at scale. You can just plot the loss that you calculate through training. And so this looks, actually quite different from what you would see during training, in that there are, all these traces that are not converging down to the lowest values. And this is just across different initializations. But when we work with typical neural networks, we use random normalized starting positions, right? We don't start on these special grid positions. So we need to randomly initialize things, and just for fun here, randomly doing things in JAX is actually quite a bit more challenging than it is in other frameworks. You have to be very explicit about where you're being random and non-random. But once I did that, it was pretty straightforward to do once I figured out how to do that, it was pretty straightforward to do random initializations, and things look actually quite a bit different. So this is, I think, the same number of initial trajectories, or at least the same number as the number that I plotted the loss of before. But now we can see that actually, none of them are going towards that center value, and all of them are actually starting off at lower levels and going down to at about the same height. So this is also something that we see in other neural networks, in bigger neural networks, so long as we're careful to randomly initialize and we're careful to set that scale in a thoughtful way. So to make sure that things are not just random, but also normalized. If you look at the starting positions of those, you'll see they form a nice circle in the XY plane. And training looks much better. It looks, they all seem to be going down to the same value of the loss. Perfect score of 0. Seems like things are going in that direction. And one interesting thing here is that you can see one gets a little bit stuck. So it heads towards that center there, actually. Maybe if we head back a slide, you can see that a couple of these trajectories head towards the center of the they head towards the center of the parameter area, and they before heading down and joining the rest of the trajectories that are going to the correct solution. So that's what this trace here represents. That's one of those examples. And this is something that we do also sometimes see when we're doing when we're applying neural networks at scale. We see sometimes there are trajectories which get stuck for a while before jumping off of a cliff. So it seems like they're probably doing something kind of similar to what's happening in this problem, where there's a solution that is close to the that looks kind of like this one, that has this kind of Pringle shape, where in one direction the loss goes up, and in one direction the value goes down. If you'll give me just 1 second, I'm going to try and get rid of this a little pop-up thing down here. Sorry about that. All right, well, that did not fix it, so I'm just going to keep going. Okay, so that's another little phenomenon that we can see in this simple problem. So due to the simplicity of this loss, we can actually also calculate all the possible solutions. So at all of the solutions, it will be the case that the gradient is 0, right? So we want the gradient to go down over time as we're optimizing, and that when the gradient is 0, that could be because we're at a solution. At least all solutions will have gradient 0. So let's check what are some values that'll give us gradient 0. Well, we'll apply it to that to the value of the gradient, which we can calculate by hand. It's relatively straightforward. I skipped the math here just to keep things going forward. And unsurprisingly, it's going to happen when theta 1 and theta 2 are multiplied together equal 1. So that means that if we multiply the input by those values, we'll get 1. We'll get the same value out as in. And so those are our solutions. And we can actually calculate those. And the code there at the bottom now shows how you would calculate the positions of all of those solutions, x and 1 over x for positive values of x and for negative values of x. And now we can actually visualize that solution set. So we can see that what's happening is that gradient descent is taking us towards that solution, and not towards that the value in the center where both of the parameters are 0. So we can see that they're landing at different points on that solution set. And interestingly, they're landing on both the values that are positive and the values that are negative, depending on where they were initialized to. So the interesting thing about that solution set is basically one corresponds to flipping the value and then flipping it back to multiply by 1. And one corresponds to just, multiplying it by 2 positive numbers, not flipping the sign. And so what's interesting about that, there's a couple of interesting sort of, takeaways I see. One is that only one of those solutions is one that a human would have thought of. I wouldn't think I've been given 2 numbers to multiply by to get 1. I wouldn't think of using 2 negative numbers to do that. That wouldn't have immediately jumped out at me. But neural networks can find solutions that are very unintuitive to humans. And the other side of that is also that neural networks don't tend to find the simplest solution that maybe humans would immediately jump for, which is to make both of those values equal to 1, to make, theta 1 and theta 2 both equal to 1. So you're just multiplying by 1 the entire time. That's not something, there's no obvious reason for neural networks to do things the simple way. And so if they can avoid doing things the simple way, they'll do it. So I think that's another nice lesson about the way neural networks and machine learning work that you can take from this simple example. The other kind of fun thing about this is if you look at those, they've got this nice shape. They've got this nice hyperboloid shape, those solution values in green in that chart. And that is, it's not a coincidence. I can take any solution. I can get another solution by multiplying one weight by a value a and the other weight by a value 1 over a. So that allows me to move along that curve there, or to switch sides if I use a negative sign. And so there's a very clear algebraic and geometric structure to this set of solutions. And that's something that generalizes to more realistic settings as well. So for rectified linear networks, if you make them big enough, they actually have that same algebraic structure. It's called a Lie group, and it's in fact a Lie group based off of the linear group. And so, so long as your network is really, really big and uses rectified linear units, then it will have something like that. You can do the same thing where you switch between the possible solutions in that fashion. The other thing is that those were essentially two separate basins. So what I mean by basin is if you look at those two sets of solutions, they're separated by a hump in the middle. The hump isn't that high, especially relative to the really high values of the loss, but there is this nice hump there that would be hard to get over with gradient descent. And so solutions in different basins can indeed have very different representations and sort of performance, even when they're separated by only a small barrier. So this is something that people have found by looking very closely at ensembles, or at least smartly ensemble neural networks. And then also I used a sort of high dimensional version of this same problem to improve techniques for finding zero gradient points of neural networks. So finding all the places where the gradient is zero, they're called critical points of the loss. And it's something that's really useful for understanding optimization. I used this multiplying by one example and its higher dimensional analogs to understand the problem of finding critical points better and to develop better solutions. So in general, the takeaway here to remind is that you can use simple problems like this one to build your understanding of how a complicated thing works. Useful ideas and technologies like neural networks are usually compositions of simpler pieces or scaling up those simpler pieces in some way. And those simpler pieces tend to admit base cases that are particularly intuitive or easy to understand. And so the last I guess the last thing is, of course, you want to combine that with pathological counterexamples. So, we've got an example like this where things are all looking nice, working nicely, and things are very straightforward and easy to work with. Then you've got your pathological counterexamples like the memorization task. And then you've got this nice 1-2 punch for tackling difficult concepts. And this general approach, I think, applies to things not just machine learning, but more broadly in both software engineering and in math. So I'll take a second to answer some of the questions that I saw in the chat there. So one question, what kinds of problems where JAX is better suited than other frameworks? So that question, that's an interesting one. I think right now, JAX is more suited for if you want to do fast math that isn't well handled by the other like neural network GPU acceleration frameworks. So it's if you want to do things that it's going to be something weird that other people in machine learning are not doing. So if you want the Jacobian of your neural network, which is like the gradient, but for the outputs of the neural network as opposed to the loss, that's something that you can do really well and with it's well supported in JAX in a way that it for a long time was not supported in other frameworks. It's sort of an inheritor to AutoGrad in a lot of ways, if you're familiar with AutoGrad, which was the automatic differentiation software, unaccelerated automatic differentiation software for a while there. So I would say what's most useful about JAX actually is that it's very principled and very thoughtful on a computational level. It's all about composition. It uses a lot of ideas from the theory of functional programming and from essentially category theory and these branches of abstract math. And while it might not necessarily help you directly being able to program things in JAX, the kind of mental exercise you get from it is certainly helpful. I felt like I learned quite a bit just by changing around the way that I was thinking about the various functions and pieces of my neural network pipeline. Then the last question, could you train something like a language model that has a more dynamic structure that's not neatly divisible into layers? Absolutely. Yeah, you might run it if you're sort of overriding a value over and over again. You might find that you need to write it slightly differently in JAX than you would write it in a different programming paradigm, in a different more Pythonic paradigm like PyTorch. But you can certainly do it, and you'd be able to make things, I think, very fast pretty easily. All right, so those are all the questions that I see, and it looks like it's about 6 o'clock. So I will leave you all here, and I will catch you all again, I guess. Let me throw this. I will catch you all again in 2 weeks for the next Weights and Biases Salon, where we'll have on some folks to talk about some public benchmarks in AI safety and in AI for social good in demystifying forms for political advertisements. So I'm looking forward to that salon. I hope you are too. And I